This is Ecoplast, a naturally biodegradable plastic from the earth for the earth. Ecoplast is made from natural materials like lignin, gelatin, hemp, and spent coffee grounds, which are sourced from waste products of different local industries. They can turn into a range of products and come in a range of textures and properties. The best thing about them? When you've had enough of them, just toss them in your backyard and they'll naturally biodegrade. As most people already know, plastic pollution is a huge issue. That's why many companies have already developed biodegradable plastics like PLA and PHB. The issue with bioplastics like PLA is that they cannot biodegrade without the high heat and moisture conditions of industrial composting facilities. This means that if these so-called eco-friendly materials wind up in the soil, they'll actually remain in the environment for a long time and contribute to plastic pollution in similar ways that non-biodegradable plastics already do. When our team set out to make a truly eco-friendly bioplastic, we were dead set on one thing. It had to be naturally biodegradable. To help stress the importance of continuing bioplastic research, we interviewed Alejandra Ruiz, a graduate student in design who has done extensive research on biomaterials. Here's what Alejandra has to say.
Bioplastics are important because they pose an alternative to current plastics, which have amazing properties but are incredibly pollutant to our environment and pretty toxic in multiple stages of their life cycle.
Let's take a look at the life cycle analysis of Ecoplast. While there's still energy and chemicals involved in extracting, processing, and treating the raw materials, we hope to find ways to minimize the most intensive parts of it in the future. Overall, Ecoplast has a very circular life cycle, and unlike many other bioplastics on the market, it can be composted directly, without any special conditions, back into the soil.
When brainstorming what kind of bioplastic we wanted to be, we decided hard plastic. Existing hard bioplastics on the market, such as PLA and PHA, fail to decompose in the landfill and produce methane. Durable. Another characteristic was to make it durable, make it sustainable for a wide range of application, whether enduring falls or supporting weight. Water resistant. It can enhance durability and can make it food safe. Scorch resistant. We wanted to create a bioplastic that could replace single-use traditional plastics, compostable. We aim for a product to biodegrade in natural conditions, enhancing soil fertility and promoting environmental sustainability. Energy efficient. Reduce costs and energy of the manufacturing process.
To start our process, we first decided on which polymer, plasticizer, filler, and additive we wanted to test. We tested 3 different starches, potato, tapioca, and corn, to see which would provide the strongest base to our plastic. Then we tested 3 different binders, gelatin, guar gum, and agar, to test the properties they would contribute. We added 2 different plasticizers, ELO and glycerin, to see which will add the most flexibility. 6 different fillers, walnut shells, calcium carbonate, oyster shells, spent coffee grounds, hemp protein, and Bermuda grass, and tested their properties and reinforcement of the material. And finally, we tested 1 additive, lignin, which has been studied to increase strength and antibacterial properties.
When testing our different starches, we initially researched the properties that each would provide. In our experimentation, we found that potato starch gave the best results for the plastic because it created a harder material. Next, we tested different protein binders. This consisted of gelatin, guar gum, and agar. We found that gelatin provided a sturdy and hard form and provided a plastic-like feel. However, agar and guar gum had too high of a water absorption and ended up being very brittle. In plasticizers, we tested ELO and glycerin. Glycerin proved to be a better candidate for black plastics, but we found different results depending on the ratios used. Our final ratios were 1:1 of glycerin and gelatin and a 3:2 ratio of glycerin and gelatin for different properties. For fillers, we tested around 7 different materials. A couple did not pan out, including mussels, oyster, and calcium carbonate. Our main fillers were coffee grounds, walnut shells, and hemp protein, along with Bermuda grass that we derived from our local student farm.
We do have some organic waste that we don't compost, and the main one being Bermuda grass, because if you compost Bermuda grass roots, they will not break down and they'll still be viable, and you'll have you spraying Bermuda grass to other parts of your farm. Weeds like Bermuda grass compete with nutrients and light with your crops, and Bermuda grass especially has these rhizomatous roots that spread quite effectively and can really choke out and cover other crops.
Finally, we need to discuss our main ingredient, lignin. Lignin is a huge waste product from the paper industry, wine industry, and various others. Locally, we can source lignin from excess Bermuda grass. Lignin is antimicrobial and can contribute to the hardness of our material. We can see that lignin in gelatin is more water resistant than just the gelatin.
We bury uniformly sized biomaterial samples in moistened loamy soil, maintaining environmental conditions at 20 to 25 Celsius. This method engages consumers in the biodegradation process by using green onion spores to speed up decomposition and reduce pollution. Our approach promotes sustainability and avoids harmful emissions from industrial composting, ensuring safer and more efficient biodegradation at home.
Let's look back to our goal list. Hard plastics. We achieve hardness for the solid prototypes. However, our films and leather can break under force. Waterproof. Our product is currently water resistant. However, we weren't able to make it fully waterproof. More research is needed to optimize and achieve performance standards. Shrinkage. We are developing a method to reduce shrinkage and weight loss during the drying process, but further research is needed to make flat molds or films for any prototype. Food safe. Most of our ingredients are commonly found in the kitchen and are edible. However, we need to make further research to determine if we produce cross-contamination, leakage into food, or if it can be used for food storage or children's toys. Energy efficient. We focus on using agro-waste to reduce the energy and cost and ingredients that are not chemically intense. In terms of manufacturing, we use low temp and require low energy, making it easier to scale up. This takes us to scalability. We were able to get many different types of textures and properties during the research, from which they have demonstrated that can be laser cut, extruded, and molded, opening the horizon to make more products that can replace single-use traditional plastics.